Hello everyone, welcome to Altium Academy. I'm your host, Zach Peterson, and today we are going to be doing a long-form design review for the winning submission for our Tesla Vehicle Display System Design Challenge. Now you may remember we put out this challenge a couple of months ago and we had some great submissions, and now we are going to reveal the winner in this video. We're going to see how they modernized the board, how they updated the circuitry, and some of the great things that I think they did when they updated this design. Let's jump in and get started. And now, that moment you've all been waiting for, I am very happy to announce the winner of our Tesla Vehicle Display System Design Challenge. The winner is Jivan Siddharth and the team at the Healthcare Technology Innovation Center. The guys at HTIC sent in this very nice PCB, which you can see here on screen in 3D. They updated the circuitry, they did a very nice layout, they kept the original form factor, which is fine, and we're going to jump into this design and see everything that they did to modernize this vehicle display system PCB. So here's the first page of the schematics. As you can see here, we have a table of contents. I always love when someone includes a table of contents in the schematics. It makes it much easier to navigate around the design and find what you need. And then here on page 2, we have a block diagram. You can see here that this block diagram shows that the design has been updated to work with STM32. Now, using STM32 allows us to do two things. Of course, we can interface with some of the original circuitry, but it also allows consolidation of a few things in the original circuitry down into the microcontroller, and that eliminates a couple of components. So let's take a look at what was reused, and then we'll look at some of the stuff that was updated. First, I'm coming at this, of course, from the perspective of a reviewer, and so I wanted to look at a couple of things that might need to be reviewed just in case they may not have been done correctly. So here, I'm looking at page 7 with our audio control interface. And here on this audio control interface, we have a Butterworth filter. Now, if we just go over to the original schematics and look on page 5, here you'll see that Butterworth filter and you'll see its specs. Here we have a cutoff frequency at 4K, stop band at 8K, and then overall gain at 1 volt per volt. Now, going back here, just looking at this, you'll see that there was some capacitance that wasn't included in the feedback lines for this section of the Butterworth filter. Now, does that mean it's not going to work at all? Does that mean it needs to be reviewed? Well, I would say you can, of course, change the component values in a Butterworth filter, but if you're going to do that, you should, of course, check that it actually works the way you intended from that modified circuit. So here with these modifications, this should be reviewed again, and just to be safe, if you're going to reuse it, I would just advocate to reuse the component values that are already in here. Now, aside from just omitting a couple of things on these feedback lines, one thing that I noticed is that a couple of the values for some of these passives are also different. So just going back over here, for example, you see C52 and C54. Those are different from the values shown here in the original circuit. So again, this is something that you would want to simulate to verify it actually operates to this spec. Then we see here it interfaces with this component U8. And one thing that I noticed on some of these components is that if you look at the parameters are not consistent on just a few of these components. Now, most of the components, for example, this capacitor, used parameters manufacturer and part number to indicate the manufacturer and the manufacturer part number. Here on U8, that has not been applied. And then here in a couple other places, for example, on these jumpers, that also has not been applied. So here, for example, you see that they use manufacturer underscore part number instead of just part number. So the parameterization for these components, of course, that's something you need to go back and review. And you usually notice it once you do an export of the BOM. And I think most people will then try to correct it manually. Of course, you can just correct it here in the schematic, and then that update will get applied once you do your BOM export. What are some other things that were reused? Well, let's take a look over here. If we go to the board power section, you can see here that we have an LT LT1616, and then we have an LT1767. And if I go back over here to the original schematics, we can then find those circuits, and we'll see here in this page that we find the LT1767 and the LT1616. So they did reuse U16 as it's shown here, and you can see that here in this circuit. For this one, they actually swapped this out for a fixed output versus this one, which has an adjustable output. So you can see here we have the resistor feedback network that's used to adjust the output, whereas with this one, we don't have that resistor network. That's because this is a fixed output at 3.3 volts, and you just connect directly to the feedback line. Now, one thing you'll also notice from the original schematics, if you just zoom out and scroll up, is that they have these two memory chips here in the schematics. Now, these memory chips are not very large. Of course, this design was put out in the early 2000s, so we didn't have huge memory chips back then. But these two memory chips were present to provide some memory for the existing microcontroller, because the existing microcontroller only had, I think, kilobytes worth of memory. Now here, switching over to the MCU with an STM32, this STM32 actually has that much memory built into it, so that's a good choice because it eliminates the need for these two memory chips. So we don't even see these in the updated design. So that's one reason I also think that STM32 is a good choice. Not only is it automotive grade, but it includes all of the memory that was required in order to run the original system built into the chip. Next, if I just jump over to U2 and then I compare this with the original schematics, we see a couple of other minor modifications. Just zooming in here on the LT1616, we can see that L2 was 22 microhenries, and then here on that same regulator, we have L2 being 5 microhenries. Again, this is one of those things that you would want to test or simulate. 5 microhenries is a little light compared to the original value in the original schematics, so you would want to just check that to make sure that that is an appropriate amount of inductance for this switching regulator. So overall, very nice schematics. Again, some of that circuitry was updated, some of it was reused and slightly modified, but overall it looks really good, and I like the choice of STM32. So now let's jump into the PCB layout and see what they did. Here we are inside of the PCB layout. In the PCB, we have 6 layers, and we actually have some fabrication information embedded in the PCB file. You can see here we have the layer stack up right here. It's got the thicknesses listed. We have the drill chart up here, and then we have some fabrication notes. Here, just taking a look at the stack up, we've done a signal ground, signal power, ground signal, 6-layer stack up. So that's a pretty standard stack up for 6 layers when you need to have an additional signal layer in the interior of the PCB. Now, just scanning through the different layers, you can see here, if we put this in single layer mode, we have a lot of ground pretty much everywhere, and then some big power rails here in the interior of the PCB. And then once we get up to layer 2 and layer 5, we can see it's uniform ground. Now, let me go back to layer 2 just for a moment, because you can see right here, there's this little ground island of analog ground. Now I'm going to address that in just a moment, but if we go back up to the top layer, we can see exactly where that connects. It connects to this bank of capacitors right here. Now if we zoom out, put this thing in 3D, we can see where all the connectors are located. I think those are some pretty good spots for all these connectors. Here you've got the FPC connector for a flex ribbon, which would then go over to the display. And then all of the other portions of the PCB layout are done pretty well. So first, let's take a look at what's going on with this STM32 microcontroller. So as I mentioned, you can see right here, coming off of pins 34 and 35, we have this analog ground region. So what's going on here? Well, if we just go back here into the schematic here in the power section for the STM32, and we go down here to this corner, we can see what's going on here. What they've done is they've defined a separate ground net, an analog ground net, and then they have a digital ground net. Now, if you go back and look at the MCU 3v3 net and go over here to page 5, and we just zoom over here to this regulator, you can see where this regulator is referenced, right? It's referenced to GND. And then if we go over here, we see there's this additional AGND net, and then this routes over to the analog reference and then the VSS analog. So it's essentially the ground port for the analog supply. Now, normally I would hate this, okay? And there are plenty of reasons to hate it. So one good thing that they've done here is they have placed a 0 ohm resistor between these two nets, okay? Basically, it's equivalent to placing a net tie. So at the very least, they are tied to the same potential. Basically, 0 volts on GND is also 0 volts on AGND. So that's a good thing. The next thing that they've done in the PCB layout is they've really localized this right here in this region. And then if you look on the bottom layer, you also see that there's that same island here down on the bottom. And then here is where that 0 ohm resistor is, R44. So you can see that right here in the schematic. As I said, normally I would hate this. The reason that this is probably not going to cause a problem is because you can see here what is being done with that analog net. So there's two things that are being done. Basically, it's just providing a way to control the return current for these capacitors. So you have a bank of capacitors here, and this provides a connection between ground directly through this island and then back up here to the top layer to these pins. So I'm okay with this for that reason. The other reason I'm okay with it is because if you scroll through here on the internal layers and you just select this polygon, you see that there is really only one spot where I would recommend changing the routing, which is right here for this trace. This trace is routing over a split in this ground reference. However, it has ground around it all at the same potential. So remember, this ground region here surrounding this trace is at the same potential as this ground net, and they do have a direct connection between them, between this ground via going down here to the bottom layer, through this resistor, and then back into this portion of the polygon. So not terrible. I would prefer, if I were doing this, to take this trace and just route it down here, over and up. That would be the first thing I would change. This trace is also routing over these splits in the power plane as well. Then if we just take a look at what this trace is actually doing, we see that it's coming off of one of these connectors. So it could be carrying a signal. We don't know the speed of that signal. If you are going to do this type of ground island right here, you want to make sure that you just don't do this with this signal, and instead just take this signal, route it around down over here. That way you're going to avoid routing over the splits in this ground, and you're going to minimize the number of splits that you route over here on power. So remember, it's already routing over these power splits. We would like to reduce any radiation from those routing over those splits. The way you would do that is just eliminate these splits in this upper layer on L2. So that would be my recommendation here. Now, if this trace is only carrying DC, then this is kind of a non-issue. So we don't know what this is carrying. Of course, if it were carrying a faster digital signal, this could create more of a problem. So again, I wouldn't do this. However, in this instance, there is a good chance that it's not going to create any problems in this particular design. Everywhere else that they've done this, they've done it well. And this is one of the few times I would say, yeah, it's okay to do this. So I'll be doing another video on this type of implementation at some point in the future, because it has been requested a few times. And the way the split analog and digital ground is usually done incorrectly, I would say this is like 95% correct. They're almost all the way there. just that one change on L3. The next thing that I want to look at is the audio interface, specifically over here in this part of the schematics. Here you can see we have this Butterworth filter and we have some amps, and they all share the same package. And if we just cross probe over to here, I want to see how this layout looks like so we can see how well the return path is going to be confined and whether we might have a noise problem from any other signals. So if I just turn off the filter, you can see here, this is where that amplifier package is located. So it's right here along this set of pads. And you can see here that with it being located in this corner, and if we just zoom out, it's located pretty far away from any of the other mostly digital stuff on this microcontroller. So it's up here in this corner, and if I just flip this over, you can see everything else that's around this circuit. So here we've got a couple of lines coming off of this connector, and so what I want to do is then take a look at what these lines actually are. So if I just select this pad and then cross probe, we can actually see what is going on in the schematics. Here we can see that that pad is part of a 232 interface. So that is probably going to be a relatively low speed signal. It's probably not going to have a big issue with crosstalk, especially given the fact that most of the stuff in this audio interface is directly over ground. And if we look at the thickness of that dielectric, we see that the dielectric on the bottom side is 5 mils. And we have copper pore everywhere. So we've got pretty good confinement of this trace and any noise that it might create around this trace. So I would be much less worried about crosstalk just from this signal coming up along this section of the circuit and then routing over here to the right. Same thing with this signal. So with this signal, if we just select this pad and then cross probe, we can then see that this is the other end of that 232 interface. So again, it's most likely a very low speed signal. We really don't need to worry about it in terms of interference into this amplifier circuit. So those are the two big things I wanted to look at in this layout, but looking at everything else in the layout, this is all done quite well. And if we just zoom out here and take a look at some of the fab data, this is actually a good strategy in some cases. You don't always have to put everything into a Draftsman document, although I really like Draftsman. If you don't like Draftsman, you can still embed all of this data into one of the layers in your PCB dock, and then you can actually export all of this so then it will appear in your Gerbers when you send your Gerber data over to a manufacturer for review and fabrication. So I think it's a really good idea to place these drill drawings and the stack up drawings, and you can actually place these as objects in Altium Designer. So for example, if I just right click here and then place, you'll see these options for example, drill table view, layer stack table. That's how you create these objects here. You don't have to draw these out by hand. Here we also have fabrication notes. As you can see here, these are pretty standard fabrication notes. If I just turn on single layer mode, you'll be able to see this a little bit better. All of the stuff that is in here is pretty similar to what I've put out in my sample fabrication notes document. So check out the link in the description. You'll be able to get a link to a Google Doc that has similar fabrication notes in it, and you can use those in your own designs. So all of these are pretty standard. One thing we don't see is assembly notes. So for example, I don't see any note in here about RoHS. Oh, no, I take that back. We do have a RoHS note right here. Very good. So those are the kinds of things you would want to put in here for assembly as well. Here we have a fabrication note for IPC A600. I don't see anything about class 2 or class 3 qualification here. That would be something more for the assembly side. So those are a few things that you might want to add. Usually that's something you specify with the manufacturer when you're getting ready to put it into production. So other than that, I like all this fabrication data, and they actually produced a pretty comprehensive fabrication package. So if we go into the archive that they created, they actually created all of these fabrication outputs and sent those in as part of the challenge. So good job on being very thorough and creating all this stuff. I did check this before starting this video, and all of this stuff checks out. So great job on all of the extra work putting all that together. Last thing I want to do before we wrap this up is just a quick DRC. The reason I want to run this is because I can't tell you how many times we get designs sent in for the 1-minute design reviews, and they haven't done a DRC clearance. So let's take a look with running a design rule check. And there we go. 0 rule violations, 0 warnings, 0 waived errors. Good job, guys. You've solved all of the outstanding problems and sent in a design that is complete. Last thing I'd like to note here is also, you can see here we have direct connections between some of these through holes and the internal polygons. When it comes to making these direct connections between through holes and internal polygons, especially when you have polygons spanning multiple layers, I would prefer to do thermal connections for these through hole components. You don't need to do it on all the vias, but I would say on these headers, definitely should do it on these headers. So whenever you have these ground connections, particularly on this component, and I'm sure you can find some others if you zoom through here, such as right here on this switch, I would say apply the thermal relief, and that will aid through hole soldering when this board goes into assembly. And if we take one last look in 3D here and we just turn off the 3D bodies, going through here and taking a look around, we do see that we don't have any obvious silk screen problems. This all jives with what we saw in the DRC check. The one exception is right here with this switch. This switch does have a footprint where the footprint silk screen is extending off the board. However, that is probably going to just be clipped off by your manufacturer when they do a review of your files, and you don't really need to worry about it. Here, just zooming out, if we just scan around, I see that we have our pin 1 markings in various locations. You can see it's right here for the microcontroller. You can see we have it here on the diodes. The polarized capacitors have their polarization markings. The inductors even have pin 1 markings, so on and so forth. So overall, a very thorough set of CAD data for this design, and I think this is done very well. So congratulations again to the guys over at HTIC. Very happy to accept this submission for our Tesla Design Review Challenge, and I thought this was a great job, guys. So I'll be reaching out to you soon to give you some prizes, and we hope that you will participate in our next design challenge. Thanks for watching this video, everybody. We love doing these design challenges. This is the second design challenge that we've done, and I'm sure we're going to have many more in the near future. So make sure to hit that subscribe button, hit that like button, leave a comment in the comments section, and of course, leave your questions. We love getting your questions, and we do our best to take some of the best questions and turn them into videos whenever we get them. Hope to see you all participate in the next design challenge, and of course, last but not least, don't forget to call your fabricator, folks. We'll see you next time.